Well, in this new playlist, I want to explain hidden Markov models, which is really important in machine learning. For example, you can use it for many different tasks, such as part of speech tagging, named entity recognition, and simultaneous relation extraction, of course. If you're a roboticist, you can use it, for example, knowing, for example, the color, just observing the color of your carpet, and infer what is hidden. I mean, what is hidden is your location. You don't know where you are, and it has many other applications. So a good way to start hidden Markov model if you are a beginner is chapter 8 of this great book by Daniel and Martin. Also, Mark Stamp. This is a really good introduction to hidden Markov model. The book of Kevin Murphy is great for probabilistic machine learning. And so what is a Markov chain? Markov chain is specified by the following components. We have a set of states. We go there. These are a set of states that we don't know. They are latent variable. We call it hidden variable. And there are, we call it Q. So Q1, Q2, Q3, and so on, Qn. And also we have some, so this is a Markov chain. But in the next slide, I will be talking about hidden Markov model. So in this Markov chain, you can watch my playlist, my Markov, for my Markov chain playlist. So let's skip it. Hidden Markov model is that we have a set of states, Q1, Q2, Q3, Qn. We don't know about it. For example, they are part of a speech, or they are named entity, and in NLP, and we don't know them. But what we can do is we know for example, some observations that, for example, we know the words. So these are the words. And then condition and then states we can see. So the direction in hidden Markov model is like this. We have some observations. But in conditional random field, it is undirected, so there is no direction. But in hidden Markov model, we have directions, these directions going downside, and so there is a difference between hidden Markov model. Hidden Markov model is generative model, while conditional random field, if you watch my playlist for conditional random fields, it is a discriminative model. But hidden Markov model is harder because it's a generative model. You should know the probability. And the probability distribution, the initial probability distribution is this. So we should, when we say training, we should learn these transition probabilities. And when we go from one state to the other state. And also these, so going from state, these green arrows are emission probabilities, or sometimes called observations, or emission probabilities, observation likelihood. But if you go from left to right, connecting the states together, it's a transition probabilities. It's A. And so our goal is to, in learning, we want to learn these parameters A and B. And of course, our observation is O1, O2, O3, because we have the words of a sentence, for example. Or we know, if you are a roboticist, we know the color of your floor of your department, if it is moving, what is the color of that? We observe it because it has a camera, it observes that. But it doesn't have a GPS, for example. A robot in an apartment doesn't have a GPS. So it wants to infer where it is based on the color of the carpet. So an easy example is is this. So Jason Eisner, he wanted to know what is the he wanted. So you cannot find records of weather in Baltimore, but you can understand, for example, Jason Eisner diary, for example, how many ice creams Jason ate every day that summer. And from that, you want to infer that, for example, it is a cold day, it is a hot day, or it is a cold day. So our observations are just the number of ice creams that he has eaten. But what we want to infer, if that is a hot air or a hot day, or it is a cold day. And of course, this is the initialization. We have initial distribution. We don't know about it. So it's a prior. If you're familiar with Bayesian frameworks, it's just a prior. So there are three problems you should be careful when you're talking about these structured predictions. For example, a kind of structured prediction is this hidden Markov model. And here we have three problems. Forward algorithm, because when you want to know what is the probability of observation, for example, a sentence given your model. Lambda is the parameters of the model. As I said, A is transition, B is emission probabilities. And the second one is Viterbi algorithm. Now that we want to discover the best hidden state sequence. And the third problem is you want to learn the parameters of your transition and emission probabilities. So we will go through them one by one, and we will solve them. And there are three different problems. So problem one. What is problem one? As I said, we want to know probability of observation given your model. What is this probability of observation given your model? Given your model, I mean, you know the transition probabilities, you know the emission probabilities. What is the probability of observation now? So we just multiply them, probability of observation 1 given Q1, and we multiply them. But it is hard to compute, so we don't actually know what the hidden state was. And so we can sum over, it's marginalize that. So instead of using such an extremely exponential algorithm, just like in computer science, we don't like brute force. It takes time, computationally expensive. So let's appreciate the beauty of dynamic programming, which is one of the cornerstones of all computer science. So what we should do is we create a data structure, for example here, alpha Tj, this alpha structure. So it represents the probability of being in state J, this is state J, after seeing the first T observation. So this is how we define it. The probability, that probability, you can relate it to the previous probabilities because it's a graphical model. So you see not only B your emission probability. So this is emission. This is A is transition, and alpha is in the previous step. We are connecting to so this is the cornerstone. This is the important idea that if you understand this, then you're done. You know the forward algorithm. So you see the probability, they are just multiplication of them in order to construct the alpha Tj. And so this is the forward algorithm. Yeah, as I said, you multiply the transition to the emission and then the alpha in the previous step, you get the alpha in the next step. And you iterate, though you can calculate and save all of the alphas. So you see, this is a forward algorithm. Alpha is just the probability observation, and QT is on state J. And at time T, you are at state J. But we don't want alpha, we want P of observation. What is the probability observation? Not just one of these QT, observation and QT. So we marginalize that. So we sum over all alphas and we get, so after calculating alpha, you just sum it and you're done. You get the probability of observation sequence. But we have another problem, Viterbi problem. In problem 2, because now that we have learned everything, we know the parameters, transition probabilities A and B emission probabilities. Now we want to find the most probable sequence of states. Again, we create a data structure. We say what is the probabilities of your states and observations, and also the state at time t is J, given your model. Lambda, as I said, is the A and B transition and emission. So again, we need to create a recursive formula, and this is that recursive formula. It's the same, but we just have maximum as well. So the intuition behind that is this. So the best, you can also calculate the best score, and you do backtracking. This one is decoupled from VTJ, but you need it because you need to save the arc maximum of that. You don't care about maximum, you care about arc maximum. So at each step, you also save it in your database and store it in your computer. So this is backtracking. Just save it what you have maximized, and also the start of backtrace is depends on VTI. So the third problem, the last problem, is we use forward-backward algorithm. So now, given an observation sequence, instead of possible states, we want to learn the parameters. We don't know the transition and the emission probabilities. So how can we learn that? Again, when they say for Bonne-Welch algorithm, you should know this is the third problem that we are solving. So it's just this forward-backward algorithm, just another name. And the backward probability is beta. The forward is alpha. The backward is beta. And so we create a data structure again. And what we need in dynamic programming, just a recursion. And the intuition behind this recursion in the next slide. But after we created this beta, what we want is probability of observation given lambda. And so this is how we create the probability of observation. So recursion is just on beta. This is the backward. But here I will show you that this is intuitively, it's very easy. The beta of t plus 1 is related to bt. So t plus 1 is related to t. So we just multiply this and this and this to get this. So we multiply 3 terms and sum over them, because there are many different ways to go from state I to the next time step to the next state. There are different possibilities. So A is the expected number of transitions from state I to state J, and divided by expected number of transitions from state I. So we normalize it. But how do we compute the numerator? The intuition is that assume we had some estimate of probability that a given transition was taken at a particular point in time t, If we know the probability for each particular time t, we could sum over all times to estimate the total count. So we have a data structure, Kc I and j time t, which is the probability that qt is I, qti plus 1, the next state is j, given your observation. But we can approximate it with another term, just using simple probability, you see? We're just approximating. And if we're approximating, the not quite QCT is now this. But we want to know the probability of observation given the model is the forward probability of whole occurrence. So this is the probability of observation given your model. So the intuition is like this. The right, it goes to, this one is backward and this one is forward. But so we have alpha, beta. So what remains is just this transition. A transition times the emission of that. So this is what is remained between backward and forward. And so this is the intuition. And then you see that the forward-backward algorithm is a little bit messy. That's why people who want very fast algorithm go to conditional random field. That's why you should watch my playlist about conditional random field, because it is beautiful. And it is fast. As you see, many algorithm in NLP is based on BiLSTM CRF. We use hidden Markov model when we need it, because HMM is a generative model, as I said. CRF is a discriminative model. So in CRF, we get what we want, but not everything. But it is fast, and but HMM it's like a bulldozer. It gives you many power, but maybe you may not need it. And of course you see this is very, it's very tedious. And so B is the expected number of times in state J and observing symbol. This is that emission. So A was your transition. This A was transition probabilities that you normalize it. The same thing for B. B is your emission and you normalize it. So we will need to know the probability of being in state J at time t, and we call it gamma t. So once again, we will compute this by including the observation sequence in this probability. So intuitively, it's very easy to see this picture. Everything is clear. So you multiply alpha and beta and normalize it by the probability of your observation sequence. And this is the forward algorithm, A and B. Now the transition and so this is transition and this is the emission probabilities. These parameters are calculated based on that KC that I told you. And KC is, so you can see it as an expectation maximization. If you watch my playlist for expectation maximization for NLP, I explained several problems that you can solve in NLP using expectation maximization. But here is very simple. You calculate gamma t, so those variables that we've just defined. So we just defined two variables. And based on them, you calculate your transition and emission probabilities. And you iterate until convergence. You go from expectation step to the maximization step. You go there, and each time you get closer to the convergence.